A very good evening, class 12th. I am back with the D and F block of elements. The first part of the video I had not uploaded, so I am doing so now. Now this unit was unit 8 initially, but presently I think it is unit number 5 or it is unit number 4 according to the present year's book. D and F block of element has 3 parts in it. The second part is with respect to KMNO4 and K2CR207. The video is already done. You can refer to it on the channel. The third part is related to the F block of elements. That is your lanthanoids and actinoids. This video is already done. So this also can be checked out on my channel. You just need to write the topic followed by my name and it would be there for you. Agenda for today's class is the D and F block of elements, general properties of the D block of elements is what we are going to do in today's video. Fine. Now, before I move on to the properties, I need you to understand the location. In your modern periodic table, from group number 3 to group number 12 is your D block of elements, out of which you have 1, 2, 3 and 4 horizontal rows which are under this category. Your first member of the first series is called as the 3D series. The second horizontal row is known as the 4D series. The third horizontal row is called as the 5D series. And the fourth horizontal row is called as the 6D series. The first member of the first transition element, the D block series, is scandium and it ends at zinc. And for these, from atomic number 21 to 30, you need to learn them up and you should know their electronic configuration by heart. So from scandium to zinc, we will be doing the configuration after this. The second element is ytterbium, followed by the end element is cadmium. Then you have lanthanum with 14 lanthanoids which are here, ending at mercury. After which you have actinium with 14 elements here, which is your actinoid series, and then these are the man-made elements for which you may not take them into account. It is the 112 element. The 112 element is known as unbarium. So that is the element. But presently this is the location of your D block of elements and the lanthanoids and actinides belong to here. 14 members from this series are placed here and the 14 members from this series are placed here. Generally, when we talk about the D block elements or the transition elements, they are also known as transition elements. The reason why they are called as transition element is because they come in between the S and the P block elements. What do I mean by that? This is your S block of element, group number 1 and 2. This is your P block of element, group number 13 to group number 18. And your D block of element comes in between the S and the P block of elements. The general configuration of the D block of elements is your last shell has only S subshell with 1 or 2 electrons, while the last but one subshell is the D subshell where you fill 1 to 10 electrons. So you are actually not filling the last shell. You are filling the last but one shell with 1 to 10 electrons. I'll give you an example to understand this. For this particular part, let us take an example of nickel, let's say. Now for nickel, the atomic number is 28. According to the Aufbau's rule, if you fill up the electrons, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, after which you have 3d where you need to fill the electrons and it comes out to be 8. So what I was trying to say is that you are not filling the outermost shell. Outermost shell to beta bhara hua hai. You are filling the 3d which is not the outermost shell. If your 4 is the n value, then what you are filling is n minus 1 which is equal to 3 D subshell with 8 electrons. So when we talk about general configuration of the D block of elements, you are not filling the outermost S, you are filling the last but one D subshell. Talking about the definition of these elements, they are said to have partially filled n-1 D subshell. I just explained what do we mean by n-1. In their ground state, or in their most common oxidation state. So this is the type of configuration we are expecting in the element's ground state or in its most common oxidation state. Only then it will be called as the transition element. Let's do a few more configurations. This has atomic number Z is equal to 21. So if I write the electronic configuration of this element, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Now, the n-1 d subshell has a partially filled subshell in its ground state, so it is a transition element. Talking about zinc, the atomic number is 30. If I write the configuration for zinc, it comes out to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now this does not have partially filled d subshell. Now since it does not have a partially filled d subshell in its ground state. Now what is the most common oxidation state of zinc? +2, which means you can remove 2 electrons, and this is where you will make an error. यहीं पर गलती करने वाले हो. Electron कहाँ से निकालेंगे? The electrons are not to be removed from 3D. It is not the outermost shell. The outermost shell is 4s, and you will remove these 2 electrons, which means your configuration for zinc 2 positive becomes like this. Now, zinc in its ground state does not have partially filled d subshell. Zinc in its most common oxidation state also does not have partially filled d subshell. So this is not considered as a transition element. Agreed? It is placed in the d block because you're filling the last electron in the d, but it is not considered transition because it does not have partially filled d subshell. Talking about copper, the atomic number for copper is 29. So if I write the configuration for copper, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. It is an exceptional configuration where you remove 1 electron of 4s2 to 3d9 and write it like this because they become half filled and fully filled, which are more stable. Now what is the common oxidation state of copper? +2. Now if I talk about this, does it have a partially filled d subshell? No. Since it does not have a partially filled d subshell, it is not a transition element. But you can also check in the most common oxidation state. The most common oxidation state of copper is +2, which means you need to remove 2 electrons. Now where will you remove the electrons from? Outermost shell. What is the outermost shell? 4s. But यहाँ पे तो एक ही इलेक्ट्रॉन है. You require to remove 2 इलेक्ट्रॉन निकालना है ना. तो 1 इलेक्ट्रॉन यहाँ से निकलेगा और अगला इलेक्ट्रॉन 3d में से निकलेगा. तो आपका configuration becomes 3d9. And now it becomes a transition element. So your copper is a transition element because it has partially filled d subshell in its most common oxidation state. Scandium is definitely a transition element because it has a partially filled d subshell in its ground state. Zinc is not considered as a transition element because it does not have partially filled d subshell in its ground state as well as in its most common oxidation state. Am I clear? As I said, you need to know the first series of transition elements, that is from atomic number 21 to 30. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Please learn them up and you should know how to write their electronic configuration. So argon is up to 18 atomic number, 19, 20 and 121. So while writing the configuration, you should know for 24 you have 18, 19, 20 and then 24. But here there is an exception. 1 electron from 4s goes to 3d to make it 4s1, 3d5, which is a stable half-filled configuration. So this is an exception. And the second exception I already did was copper. So let us quickly write down the electronic configurations for these. That is for if you nickel already did. Argon, 4s2, 3d8. Copper I already said is an exceptional one. Argon, 4s1, 3d10 and zinc is the last member of the first transition series which has 4s2 and 3d10. So this electronic configuration for the first series you should know. Now talking about the unpaired electrons. Till here it is fully filled. 4s2 is also fully filled. D में सिर्फ एक electron है. If you remember beta, D has got 5 orbitals. So if it is D1, it has 1 unpaired electron. If it is D2, then it has 2 electrons unpaired. If it is D3, it would have 3 unpaired electrons. If it is D4 or it is D5, then it has 5 unpaired electrons. So this is your 3D and this is your 4s. Fine. Talking about manganese. 4s में तो 2 हैं बेटा, तो अच्छा, I'm sorry. In this case, it will be 5 from here and plus 1 for the 4s, so this becomes 6. Talking about manganese, you have only 5, 4s to full hai. Now, when it is 3d6, if I fill this up like this, how many unpaired are left? Only 4. So this becomes 4. 3d7 तो एक और को pair up कर दिया. You are left with 3 unpaired electrons. 3d8, you are left with 2 unpaired electrons. 3d10, but there is a 4s1, so 1 unpaired electron. 4s2, 3d10, there is a 0 unpaired electron. Fine. So you should be in a position to write the electronic configuration and calculate the number of unpaired electrons. After which you have something called as the magnetic moment. Now the magnetic moment, to calculate, the formula for magnetic moment is n into n plus 2 under root. And what is the n? N stands for the number of unpaired electrons. So if you are given a question for chromium, please find the magnetic moment. The unit of magnetic moment is Bohr magneton. So for chromium, you very well know the number of unpaired electrons is equal to 6. So n would be 6. So your magnetic moment would be under root of 6 into 8, which will make it to be 8 6 how much? 48 Bohr magneton. I'll do one more for you. Let us do it for cobalt. In case of cobalt, if you are asked the magnetic moment, how many unpaired electrons does cobalt have? 3. So it would be under root of 3 into 5, which will be written as under root of 15 Bohr magneton. Am I clear? This is how you write the magnetic moment. Also, the paramagnetism or the paramagnetic character is directly proportional to the number of unpaired electrons. So out of these, the maximum number of unpaired electrons are for chromium. So chromium is most paramagnetic, while the least number of unpaired electron is 1 in case of scandium and 1 in case of copper. So they are least paramagnetic. Now what about this? When we talk about zinc, does it have any unpaired electron? No. Since it does not have any unpaired electron, we say zinc is diamagnetic. It has no unpaired electron and the n value is 0. Therefore, such a identity is said to be diamagnetic. Now let us do a few questions which are commonly asked. The first one is to calculate the magnetic moment for the following. We have to do it for nickel 2+. For this, first write down the electronic configuration of nickel, for which you should know the Z value is 28. Please learn up the atomic numbers of first transition series of D block of elements. This will be required also in coordination compound. The electronic configuration for nickel therefore becomes argon 18, 19, 20 and 8 here 28. Now after this you need to remove 2 electrons. So if you have to remove 2 electrons, you will not remove from here, because this is not the outermost shell. The electron removal is going to be from 4s. So your electronic configuration in that case becomes argon with 3d8. Now let's talk about the magnetic moment. For the magnetic moment, you need to know how many unpaired electrons. You can do it with the mantle maths also. But if you want to do it your way, then it has to be 1, 2, 3, 4, 5, 6, 7 and 8. How many unpaired electrons left? N comes out to be 2. So the Bohr magneton for nickel 2 positive is going to be under root of 2 into 4 under root, and the answer is under root of 8 Bohr magneton. Am I clear? While if I talk about chromium 3+, please write the configuration. Chromium has atomic number of 24. And the configuration for chromium is exceptional with 4s1 3d5. Now if you want chromium to lose 3 electrons, one would go from 4s and 2 would go from 3D. So the configuration in this case would be written as argon. 1 electron gone from here, 2 electrons gone from here, you are left with 3D3. With 3D3, the number of unpaired electron becomes 3, and if you calculate the Bohr magneton with n into n plus 2, that is 3 into 5, the answer would be under root of 15 Bohr magneton. Am I clear? There's another way of asking the same question. For a divalent ion क्या होता है? Plus 2 charge, 2 valency of an element with atomic number 25. Now what is element with atomic number 25? वो पता हो तब तो. Z25 is for manganese. And we are talking about manganese ka plus 2, and you need to calculate the Bohr magneton. That is the magnetic moment. The first thing that you need to do is write the electronic configuration for manganese, which is argon 4s2 3d5. Now you need to calculate the electronic configuration of Mn2 plus. 2 plus means you will lose these 2 electrons. Therefore, you are left with argon 3d5. Therefore, clearly means N is equal to 5. There are 5 unpaired electrons in this manganese with plus 2. So, the magnetic moment will be 5 into 7, that is under root of 35 Bohr magneton. Already told you the formula for magnetic moment is N into N plus 2 under root. What is N? N is the number of unpaired electrons. The last question, trivalent, matlab plus 3, for an element with atomic number 26. So if the atomic number is 26, your configuration is argon 4s2 3d6, and actually this is iron. Now for a plus 3 oxidation state, you need to make it lose 3 electrons. Now where will the 3 electrons move from? Please do not make an error. 2 electrons from here and 1 electron from here. So your answer for Fe3 positive will be 2 gone from here, 4s left, and 1 from here, you're left with 3d5. Unpaired electrons are 5. Therefore, the magnetic moment will be 5 into 7. That is again under root of 35. Bohr magneton is the answer for the question number 4. So this is how the questions are asked on the magnetic moment, where you need to write the electronic configuration, followed by calculate the number of unpaired electrons, and then substitute in the formula. Do not forget the unit. Coming to the next property after the magnetic property is the melting point. This is the graphical representation given in your book. Now, melting point and atomic numbers. There are 3 lines in the graph. The lowermost line is for 3D elements, the first transition series. The second green colored line is for 4D elements, the second transition series. And the third line is for 5D elements, the third transition series. In these 3 lines, as you can see, the melting point is increasing. If the melting point is increasing, means the interatomic attraction is increasing. Now we are talking about metals. In this, as you can see, generally speaking, the melting point initially increases and then goes to the maxima and then goes falling down. Melting point generally increases, then there is a dip in case of the second series, and then it decreases down. In the first series also, it first increases and then there is a, these are exceptions. Technetium and manganese, these 2 elements are exceptions. If I forget them, then generally speaking, the melting point increases and then decreases. When we talk about melting point, what does the melting point depend on? Interatomic interactions. Now what are the atoms? They are metals. So we are talking about intermetallic attractions. Now what is the bond between metals called as? The bonding between metals is called as metallic bonding. So if you have any metal in solid state, it is a hard solid if the metals are tightly bound to each other. It is a soft solid if they are loosely bound to each other. This interaction between metals is called as the metallic bonding. Now what does this metallic bond depend on? Metallic bonding is done by the number of outermost ns electrons plus the unpaired electrons of the d subshell. Which means if we look at the electronic configuration, in case of tight scandium, the outermost 2 electrons from here and 1 here, 3 electrons will be utilized in metallic bonding. In case of titanium, 2 electrons of the outermost shell and 2 unpaired electrons of the 3D will be utilized. 4 electrons are utilized. Vanadium, 2 from here and 3 from here, 5. Chromium, 1 electron from here, 5 electrons from here. So 6 electrons are utilized. So the number of electrons utilized in metallic bonding are increasing. But as soon as you start to pair it up, then in that case, the number of electrons participating in metallic bond for iron would be 2 from the outermost shell, but only 4 from here because the paired electron do not participate from the 3D. So there are again a total of number of decreasing. So when the d orbital starts to pair up, then in that case the number of electrons participating in bonding goes on decreasing. So initially the number of electrons participating in metallic bond increases and then it decreases, and that's the reason for your V format of the curve of melting points. Now these metals are bound to each other by some attraction which is called as the metallic bond, and this metallic bond depends on the unpaired electrons of the d and the outermost 4s electrons. So more are these number, more is the metallic bond. Now what is so special in manganese? When we talk about manganese, the configuration is argon, 4s2, 3d5. Now these are outermost electrons, they participate in metallic bonding. But the melting point is low. Why is the melting point low? Because maybe that these 5 electrons resist to participate in metallic bonding because of stable half-filled EC. That is why these 5 electrons may not be participating. That is why we get a lower melting point in case of manganese. So in case of this element also, again it is because of the 4d5 which is sluggish in participating that there is a dip here. Now when we talk about here, in case of 5D series, this is the large in size series. If it is large in size, ionization energy is low. Means electrons can easily be used up for metallic bonding. So the last series has strong metallic bonding. Because of its large size, electron utilized for metallic bonding from the valence shell and the n-1d is easy. So since the metallic bond are strong, therefore the melting point is also large. Agreed? So as we go from 3D to 4D to 5D, the size increases, ionization energy decreases, electron participation for metallic bond becomes easy. So the melting point of the third series is much higher as compared to second, as compared to first. And what could be the reason for this dip in the center where you have a D5 is because of a stable configuration of D5. They are reluctant in participation in metallic bond. Also at times after copper, you also have zinc. In case of this, you also have mercury and you have cadmium. Now these are low melting in nature. In fact, mercury is a liquid. And what could be the reason for it? Why is mercury a liquid? Mercury is a liquid because of weak metallic bond. Now all these 3, that is the last members of the series, all of them would have D10. Now since they have a D10 configuration, means they will not participate in bonding. So what is participating in bonding is only the 4s, which is going to be very less. So in the last members of each series, they are soft metals. So zinc is said to be a soft metal because of weak metallic bond, and weak metallic bond is because of the 3D10 configuration in zinc, which do not participate in metallic bond. So all the portions of this particular graph I have already done. These are soft metals. Initially, why is there an increase in melting point? Because the number of unpaired d electron increase, they participating in metallic bond. Why is there a dip in the line? Is due to the D5, which is reluctant in participating in bonding because of stability. So the melting point becomes weak. So the melting point is weak, metallic bond is weak, so melting point is low. And once the electrons start to pair up, they do not participate in bonding. Only unpaired electrons of the n-1d participates in bonding. That to the metallic bonding. Moving on to the next property, which is enthalpy of atomization. What do we mean by enthalpy of atomization? Energy required to isolate an atom from the solid state. It is represented as delta HA, enthalpy of atomization. The curves for enthalpy of atomization resemble that of melting point. Again, they are mountain type curves with a dip here and a dip here and a slight dip here also. So if you have to remove an atom, let's say I want to remove this atom from a solid metallic lattice, I will require energy because I will have to break, all the metallic bonds are to be broken for me to remove this atom from its lattice. And to do that, I need to locate the strength of the metallic bond. If the metallic bonds are strong, the energy required to remove this atom is going to be large. So your enthalpy of atomization directly depends on the number of metallic bonds formed. The metallic bonds depend on the outermost s electrons and the n-1d unpaired electrons. Also the interatomic attractions, that is the intermetallic attraction or the metallic bonds. So enthalpy of atomization increases as you go from D1 to D4, and then at D5 generally there is a dip because these is a stable electronic configuration reluctant to participate in bonding. And then from D6 to D10 again there is a decrease in the metallic bonding because the electrons have started to pair up. Fine. So the answer for enthalpy of atomization and metallic bonding are parallel. The key words are these three whenever we talk about enthalpy of atomization. Fine. Also, the enthalpy of atomization would be for 4D it would be larger and 5D would be the largest because here the size is large, ionization energy is low, therefore metallic bond is strong because the electron participating in the bonding are easily removed from it. So you have a strong metallic bond formed by the 3D. That is why the enthalpy of atomization is higher in 5D. Okay. Moving on to the next graphical representation from your book is about the atomic radius for the 3D, 4D and the 5D series. The radius is increasing as you go from 3D to 4D to 5D. The size is increasing. In the 3 rows they are moving up. But you can see there is a very small increase as you go from the second transition series to the third transition series. In fact, there is no gap here. But as you go from the first transition series to the second transition series, there is a large increase in size. And the size increases because as you go from 3D to 4D to 5D, your n value is increasing. So the number of shells increases. Therefore, the size increases or the radius increases. Agreed? So as you move from 3D to 4D to 5D, n value increases, that is the shell value increases, and hence the size also increases, the radius increases. Now, why is it again a curve? The curve reason is as you move from scandium to chromium, we find the size is decreasing here. Then it becomes kind of constant, and then there is a slight increase in size. This is important to understand. The reason that is attributed is as you move from D1 to D5, you have your nuclear charge is more than electron-electron repulsion of the D subshell. So if the attraction is more, the size decreases. When we move from D5 to D10, you have an almost constant size because the nuclear charge is almost balanced out by the electron-electron repulsion. Why am I talking about electron-electron repulsion? In your D subshell, 1, 2, 3, 4, 5, you have 1 electron in each subshell. So repulsion is not there. As you increase this, protons are also increasing. So nuclear charge is increasing and the electron repulsion does not happen. So the size decreases. But no sooner you begin with D5, say D6, D7, D8, there is electron-electron repulsion which starts off because of crowding In the 3D subshell, you are adding more electrons and there is some amount of repulsion between them, which balances the nuclear charge as you go from D5 to D8. Now, when you come towards D9 and D10, towards the end, we find that your electron-electron repulsion is much more than the nuclear charge. So, this leads to increase in size. So, the conclusion is, initially there is a decrease in size, then it remains constant, and then there is an increase in size. So, on an average, the sizes of transition elements are almost similar because it first decreases, then it is constant, and then slight increase. So, on an average, if we talk about the elements of a series, we say that their sizes are almost similar. They have similar atomic radii in a particular series. Fine. Now, talking about if we go from 3D to 4D, there is a large gap. But between 4D and 5D, there is a negligible difference. And the cause of this is your lanthanoid contraction. In between your 4D and the 5D series, you have lanthanoids. Let me show it to you. This is your 3D series. As you go from 3D to 4D, there is an increase in shell, so size increases. But when you move from 4D to 5D, there is a presence of 14 lanthanoids. And the lanthanoids cause an effect on the size of the 5D series. Lanthanoid, there is something called as a lanthanoid contraction, which you can refer to in the third part of the video of this chapter, where I have dealt with the lanthanoid contraction, and it is because of these lanthanoids that the size between 4D and 5D does not change much. That's the reason you have a similarity in the size of 4D and 5D here. These two lines are almost very close, showing that the size of elements of 4D series and 5D series are almost same. Since the sizes are said to be almost same, the reason is because of the presence of lanthanoids, that is your 4F in between 4D and 5D, and 4F has a very poor shielding effect. It increases the nuclear charge, hence the size decreases. So even if you go from 4D to 5D, there is an increase in shell, but the size does not increase much. A commonly asked question from this section is, the size of zirconium and hafnium is almost similar. And the reason attributed here is we talk about lanthanoid contraction. Fine. Moving on to the next important property, which is multiple or variable oxidation state. Transition elements are found to show a variety of oxidation states. The reason is the general electronic configuration is N-1D has 1 to 10 electrons and the outermost S has 1 and 2 electrons. Now the energy gap between these two is very low. A very small energy gap is between NS and your N-1D. So what? Which means these electrons can be easily lost because they are outermost. But these electrons can also be lost because the energy gap is very low. So if these can participate in bonding, these can also participate in bonding, which means there are a large number of electrons which can participate in bonding. Therefore, it leads to a variety of oxidation state. If only NS participates, then the oxidation state would be +1 and +2. But if these also participate, then it could go to +3, +4, +5, so on and so forth. So the conclusion is, a small energy gap between NS and N-1D subshell causes electrons from both these subshells to participate in bonding. That is why you have a large number of electrons, a variety of electrons participating in bonding, and that's the cause why transition elements show you variable oxidation state. And to recall, you very well know, iron exists as ferrous as well as ferric, copper exists as cuprous as well as cupric, manganese is the in lead, you see it as +7 in KMnO4, you see it as +2 as your titration product. You also have an Mn+4, the brown colored product formed during titration at times. So there is a variety of oxidation states in case of transition element owing to the participation of outermost S and Last but one, d subshell electrons. Moving on to the next property of transition elements is formation of complex compounds. Now the complex compounds are same as your coordination compounds. And coordination compounds have a coordinate bond formed. Now for the coordination compounds, you need a coordinate bond. As you very well know, coordinate bond is formed when there is a electron pair, that is the lone pair donor should be present. And such a lone pair donor in coordination compounds is known as a ligand, which means a compound like ammonia is called a ligand because it has a lone pair to donate. A compound like water is also called a lone pair donor because it is again has got two lone pairs, so this is also known as a ligand. Now these identities donate electrons to transition metals. And what is so special in transition metals that they are able to form a coordinate bond with the ligands? The answer to this is they have a small size because of the presence of d subshell, which has a poor shielding effect, causes the nuclear charge to increase, so their sizes are smaller. High ionic charge to attract the ligands. You very well know they show multiple oxidation state, so they have more amount of positive charges to attract the lone pair towards themselves. Also, this lone pair is to be shared with the transition metal, and the transition metal needs to have a vacant orbital to share the lone pair. So there is an availability of vacant d orbitals for the lone pair donation or a coordinate bond formation. So the three reasons why transition elements form complex compounds or coordination compounds is because of the transition metal's small size. So they form a strong coordinate bond. A very high ionic charge because they use their ns electrons as well as n-1d electrons in participation. Also, availability of a vacant orbital for the lone pairs to be donated is the cause. This can be understood a little better when you go through the coordination compound introduction on my channel. You can check out that particular video for coordination compounds chapter, the introduction part. You would understand it a little better. You can also do coordinate bond video which was done in class 11th chemical bonding chapter. This particular video is also available on the channel in case you are struggling with coordinate bonds. Fine. So transition metals have a property of complex compounds or coordination compounds. The next two properties are alloy formation and interstitial compound formation. Now when we talk about alloy formation, it is something like a transition metal iron combining with nickel to form stainless steel, let's say like this. Now if that has to happen, and if you have a solid of iron where iron atoms are bound to each other, since the sizes are similar, you can easily replace an iron atom by nickel somewhere here, and you can replace another iron atom by chromium somewhere here, and they can easily replace each other and form a homogeneous mixture. And that is the reason for alloy formation. Alloys are easily formed because of similarity in the atomic radius of transition metals, and they can easily substitute each other in the metallic lattice. As we already did, the sizes of transition elements are similar. I explained this property a little while back, that their sizes are almost similar, so they can easily replace each other in the metal lattice. So in a homogeneous mixture where you have iron, nickel and chromium, they can easily replace each other in the solid state and lead to the formation of an alloy. Fine. Talking about interstitial compounds, have a close look at these sites, the gaps. These are called as the intersites. In these gaps that we have, easily small atoms like hydrogen, carbon, nitrogen can go and fit into these gaps. So interstitial compounds, interstitial sites are these, the gaps in between the metal atoms. Small atoms like hydrogen, carbon, nitrogen, etc., they are trapped in the lattice of metal, somewhere in between. Now these compounds are non-stoichiometric, which means there is no particular ratio as to what is the ratio of hydrogen to iron, or how much carbon in terms of hydrogen, or how much carbon in terms of iron are present. There's no formula for it. It is neither an ionic bond is formed, neither a covalent bond is formed. They are just present in these pink areas that I have just mentioned. You will find small atoms like carbon, hydrogen, nitrogen are found in these gaps of the metal lattice, just present there, just sitting over there. Since they are sitting over there, now whether they are sitting in all the gaps or they are sitting in a few of the gaps, they do not form any type of bonding, which means any number can be present. And that is the reason there is no fixed formula of the interstitial compounds. Of course, we see that due to the presence of these atoms in this, it becomes harder, and the melting point also increases because of there are no gaps left in between them. Also, conducting nature stays and the chemical inertness is also there. So, interstitial compounds are formed when small atoms trap themselves in the intersites because of their sizes matches with the size of the gaps. Only then it is possible. And just they are trapped there, they're just present there. No type of bonding takes place. Fine. Moving on to the next property, which is the catalytic property. This is again an important property of group number 10 elements, which is nickel, platinum and palladium. This group of elements is found to show catalytic properties in the periodic table. Now, what exactly happened? Let us say I have a reaction of H2 plus I2 and it forms twice Hi, and it is a slow reaction. Now, if you add a catalyst, then in that case, what exactly happens? The catalyst binds to the reactants to form a transition state or an intermediate state, and then quickly helps in bond breaking to lead to the formation of products. So the function of catalyst is, number one, to bind to both the reactants, bring the reactants closer to each other, and then lead to product formation. It provides a surface area where the reactants can bind to it. Also, it speeds up the reaction because it decreases the activation energy. This concept was done in Chemical Kinetics chapter number 3, where activation energy was taught. You can go through that particular topic before coming to this property. So, transition metals act as good catalyst because, number one, they lower the activation energy. Since the activation energy is lower, the reaction becomes faster. Secondly, they show multiple oxidation states, so they bind to reactants, leading to increase in concentration of the reactant on the metal surface. The reactants bind to the catalyst brings them closer. Hence, it weakens the bonds in the reactant molecules, hence leading the reaction to be faster. So, the keywords, if you are asked the two main reasons why transition elements act as good catalyst, your answer should be they show a lower activation energy, and also they show multiple oxidation states to bind to the reactants, leading to increase in concentration of reactant molecules on the metal surface. So these are two important reasons for it. Fine. The next is a tricky property called as the standard reduction potential, which is represented as an E naught values. For the transition metals, standard reduction potential means your metal ion accepts electrons to become a metal solid. We observe that all the values are negative, below 0. If the values are below 0 means the standard reduction does not happen. They prefer oxidation. But the only element which shows a positive value is copper, which means there is something special about copper that it shows a value higher than 0, hence it prefers reduction, which means your copper accepts electrons to become copper solid and your E naught value is a positive value, therefore this particular reaction takes place. Now to justify why does copper have a higher reduction potential value or a positive reduction potential value is, reduction potential is not merely gaining electrons to become a metal. There are two more energies involved other than electron gain enthalpy, which of course is a negative value. There is something called as the metal ion is in aqueous medium, so there is a hydration energy involved, which is represented as delta H hydration. Also, since after accepting the electron, it transforms into a solid state where the metal atoms are attracted to each other to form a ordered arrangement of atoms, leading to a strong lattice formation. Therefore, there is an atomization enthalpy also involved. And perhaps the enthalpy of atomization, which is the positive value, is much larger than the hydration enthalpy, is the reason why copper shows a positive standard reduction potential. So your key word for the answer should be enthalpy of atomization is much higher than the hydration enthalpy, so that the net value of E naught comes out to be positive. This is the last general property of transition metals which I was doing. I just discussed two more important questions from this part of the chapter, and with that we will wind up the video. The first question is, which is the most common oxidation state of copper in aqueous medium? Talking about copper, you should know the atomic number is 29. Electronic configuration looks like this. From the electronic configuration, it is apparently clear that the electron to be lost is 4s1. So the common oxidation state expected is copper plus 1, which would have argon 18 and a 3d10 is what we expect. But if I say no, you very well know it exists as a copper 2 plus. If it has to lose the second electron, then the second electron is to be lost from 3d10, which means the configuration now should be argon 3d9. Now this is your ionization energy 2. Second electron removal energy is called as successive ionization energy, while the first electron removal is ionization 1. Always second ionization energy is larger than the first ionization energy, which we know. Removal of the second electron is difficult as compared to the first electron. Successive ionization energies are higher, is a topic done in class 11th. So second electron removal is difficult, but it still happens. How do you justify? And the answer lies in the word aqueous medium. What is so special in the aqueous medium? Your answer is, in aqueous medium, copper exists as copper 2 plus. You very well know, if I talk about copper, as you go to copper 1 plus, the size decreases. If you go to copper 2 plus, the size further decreases. Sizes of cations are lower than the parent atom. So more the electrons lost, size goes on decreasing. If the size is less, then the hydration energy is more. There is something called as enthalpy of hydration, which is directly proportional to charge upon radius. Now, if you compare the charge upon radius for cuprous and cupric, charge is more in case of copper, radius is smaller in case of copper 2 plus. So, the hydration enthalpy for copper 2 positive is going to be higher because it has a higher charge and lesser radius. So, both the factors will cause hydration energy of copper 2 positive is much higher. It is the energy released. Now, as I said, second electron removal is difficult, but the enthalpy of hydration overcomes the second ionization energy. Therefore, in aqueous medium, copper exists as copper 2 plus. So, the key word is your enthalpy of hydration overcomes the successive ionization energy of copper. So, copper easily goes to copper 2 positive, but it would happen only in aqueous medium. Am I clear? So, copper should exist as copper 1 plus, but in the presence of water, copper 2 plus is easily stabilized by the hydration energy which is released, and this hydration energy compensates for the ionization 2 energy of copper. Coming to the last question of the class. Why are higher oxidation states of transition metal found in oxides rather than fluorides? That's a good question. Higher oxidation state means more electrons participate in bonding. Now for the electrons to participate, the electrons are pulled out to form a bond. To pull out the electron, you require electronegative atom. So the electronegative atom is oxygen and fluorine. But what is found is when we talk about a fluoride or we talk about an oxide, in case of, let us say, manganese, manganese forms MnO4 minus, while as a fluoride it forms MnF4, which means manganese in this case has an oxidation state of +4, while manganese in this case has an oxidation state of +7. How come with oxygen manganese can use its 7 electrons, but in case of fluorine it uses only 4 electrons? And the answer rises is this forms only one bond, therefore only sigma bond. While when we talk about oxygen, it forms a double bond. If it forms a double bond, therefore there is a pi bond formed. And because of pi bond, there is a multiple bond formation. In this particular identity for oxides, you have multiple bond formation because it has a valency of 2. It will form a double bond. And the pi bond also helps in resonance. Then this becomes stabilized due to resonance or delocalization of electrons, as whatever may you say. So when we talk about an MnO4, the structure of MnO4 is like this, where all the 7 electrons of Mn are used up, and this then leads to a stabilized structure like this, leading to resonating structures which stabilize the MnO4 minus, which has a +7 oxidation state owing to the presence of pi bond at every site of oxygen. Whereas when we talk about MnF4, for MnF4 it would be one bond with fluorine because fluorine can only form one bond. So 4 bonds are formed. Your electrons are still left over manganese, which are not utilized in bonding. So your oxygen, due to the presence of pi bond and delocalization, multiple bond formation is the key word, which stabilizes by resonance or delocalization. Fine. With this, we come to the end of the D and F block of elements. The general properties of D block of elements is what we did today. And already on the channel, you have the part 2 and part 3. So with part 1, I complete the chapter. It was a requirement of the hour, but I had difficulty in doing that due to some of my prior commitments. But I hope with this, all of you have got enough content on the channel. Do very well in life. Stay connected. Bless you loads. Please study for your practicals also. Do well. Bye for now.